Hi, good morning. Welcome to today's webinar that we'll be talking about the Brumadinho Tailings Dam failure in Brazil. And I want to thank you for attending and also your interest in our webinars. I see a bunch of people connected today. We'll be having another webinar or another version of this webinar on Friday. It will be in Spanish, and then on Monday will be in Portuguese. It's been great. The number of registrations we've had been for this webinar, so it shows the interest of the people in this kind of events, and I hope I will be giving you some insights in regards to what the event actually was and what happened, and also what we did with the river flow 2D model. So I hope you can hear me well. If you can give me just a quick note on your questions panel or on your chat panel, just to know that you can hear me. I will appreciate that, please. Okay, so it seems the sound is correct. So I want to also to indicate that we are recording the webinar. So about an hour after the webinar, you will receive an email with the instructions to watch it online. You can share that link also with your colleagues if you find someone is interested in this topic as well, couldn't attend. So today's webinar is about, it's titled Two-Dimensional Runout Evaluation of the Brumadinho Tailings Dam Failure in Brazil. My name is Reynaldo Garcia. I'm the Director of Model Development and Applications at Hydronia. And my colleague, Adolfo Trips Correa, he's the president of Brazil Hydro and is the representative of Hydronia in Brazil. He will be presenting the webinar in Portuguese on Monday as well. So today's outline includes the brief description of the tailings dam disaster that occurred in Brazil early this year, 2019. Actually, the dam itself is not called Brumadinho, although many people say Brumadinho Tailings Dam Break. Brumadinho is a small town downstream from the dam site that is known as Córrego do Feijão, is the actual name of the location, and the dam is the Dam 1 of this location. So I will talk a little bit about that, then I will discuss what we did in simulating the dam break event with the river flow 2D model, and also how we use the different tools we have in the model to assess different scenarios with rheological formulations that are available in the model. And of course, if you have any questions, feel free to just use your question panel and post your questions there. I will be addressing some of the questions that I have time to respond by the end of the webinar. So the Córrego do Feijão dam is called also B1 Dam or Dam 1 of that mine. The original dam was built in 1976 by Ferteco Mineração. It's located near Brumadinho in the state of Minas Gerais in Brazil. And subsequently, it was acquired by Vale. It's a large company that owns many dams in Brazil and other many locations in Brazil, and it was acquired in 2001 and was used until it was decommissioned in 2014. And during its existence, it was used for the sedimentation or dumping of iron ore mine. So it's a very particular deposit because the iron ore is very heavy with respect to sediment. So this is something that you have to keep in mind when you want to simulate these kind of events, because the density and the properties that these sediments have is very different from the typical debris flow or mud flow type of events. So the dam was built initially to a certain height, but eventually was increasing height as the amount of deposits sorry increased over time using the upstream build method. So this is something that is not used so much anymore, but it's a kind of method to increase the height of the dam, and it was increased up to the height of 86 meters. The total deposited tailings area as it was at the moment of failure was close to 250 square meters, and it included a volume of almost 12 million cubic meters. As I said, it was decommissioned in 2014. It wasn't in operation, so it was completely filled. And the company that managed this mine, they had in place a number of standardized procedures to ensure the safety, or try to ensure the safety of the dam. And so it had a program of biweekly field inspections. The dam itself and the different dams that were built had 94 piezometers and 41 water level indicators. So it was relatively well instrumented. There was a mining dam emergency action plan that in Brazil is called PAEBM, and it was prepared according to the regulations. The dam had video monitoring, and thanks to that, actually, video monitoring, we have a good video that I will show in a minute that represents the actual moment when the dam failed. It had a siren alert system. It had a downstream population registration, and even there was an external emergency simulation, or this type of events that you do for preparation, that was carried out a few months before the event in 2018. So there was a lot of effort that were done by the company to try to keep the safety of this dam in place. So regardless of all that, in January 25th of this year, 2019, at 12:28 p.m., the dam failed, and it failed catastrophically, as you will see. There was a lot of damages. The area that was affected included part of the Brumadinho village downstream, and also there was a large area including part of the Paraopeba river, that is this river downstream. This is the dam location, and this red polygon indicates the area that was mostly affected, although also the Paraopeba river downstream was affected at some point. There is an estimated death toll of more than 300 people. There are still corpses that are missing, that were never found. So it's one of the biggest events that have occurred related to tailings dam failure. So this is the dam itself as it looked at the moment of the failure. It was January 1st, 2019 at 12:28. And I will show you this short video that represents the moment when the dam failed. So as you see, this is taken from downstream. If you haven't seen this before, you will note a number of things. First, it starts slowly and it starts to collapse, and this is something very particular. Some experts call this like a liquefied or static liquefaction. There are still debates on how the dam, the mechanism that generated the dam failure. But as you can see, initially it's relatively slow, but in a few seconds, maybe 30 seconds or so, you see that the dam has reached very rapidly this area downstream. And of course, it released millions of cubic meter of material that travel downstream, and this is a very heavy material, as you will see. So this is a picture, an animation that represents how the site looked before and after. This is taken from online site, and you see that the approximate area of affected by the event. This is the dam location, and this is the Paraopeba River. I will talk about this in a minute as well. So this is the location of the dam. This is the mine area. There are some mining operations around here. And you see here the town and the Paraopeba River. And this is an image of how it looked like more or less today. So you see all the area that was affected. There was a bridge that collapsed here. I will show you to you also. And there are other sites that we investigated in order to apply the model to this location. This is a view of from downstream of the dam. This is the dam site. And this is the bridge that collapsed. But you see here the scale of the event. If you look at a house, you can see that the depth that and the amount of damage is very significant. These are other locations. This is the bridge location that failed. Again, this is another pass that was covered by mud downstream. This is an area also where you see before and after. And you know, all of these crops were flooded and remained with a large accumulation of mud or iron core. So what I'm going to show you is an application of the river flow 2D model, and particularly the modern debris flow, what is called the MD module. Now I need to say that this was an application based on information and data that we collected. It's public, all the data. We didn't use any proprietary information. So it was a kind of experiment that we wanted to do to see if the model was able to replicate these kind of events and what happened. So the model, the river flow 2D model is developed by Hydronia and the computational hydraulics group at the University of Zaragoza in Spain. It's a two-dimensional hydrologic flexible mesh model that can deal with hyper-concentrated non-Newtonian fluids. It can do dry and wet areas, and the model is based on a finite volume numerical engine that can handle supercritical and subcritical regimes. And it can deal with hydraulic structures like culverts, weirs, bridges, gates. It has an internal dam bridge component as well. It's integrated with the QGIS software that is an open source GIS system that allows integration with other softwares. And what we have done is to develop a plugin for the QGIS, so you can develop all the data, the mesh, and all the necessary data within the system, and also generate the maps from the model results, including, for instance, hazard maps and animations. The model runs in standard computers, but also it can run in GPU with the GPU card. It can take advantage of GPU cards, and the advantage of using GPUs is that the model can run very fast. And how fast it can run up to 700 times faster if you had the proper card installed. You can also install the software in the cloud, and if you can build a virtual machine in the cloud to use for running the model, you only pay for the time you use the model, and then that has a very important reduction in your investments in regards to computer hardware. The present version of the river floating model runs in QGIS 3.8, and this is a picture of the user interface. It has a number of tools to generate animations, cross sections, analyze different data at different locations, and it's completely integrated with the QGIS environment. The flexible mesh that the model uses for making the computations is a triangle irregular network, and it can be adapted to any geometry. You can see here that it's adapted to an area where you have buildings, streets, and different obstacles, and you can refine the mesh around the features. The main computational unit is the triangle, and at each triangle the model computes the velocity, depth of flow, and also other, if you are running, for instance, the sediment transport component, it will also compute how the bed changes due to erosion or sedimentation. The equations that the model uses are the shallow water equations written in conservation form, and to adapt the model to handle viscous fluids, and also viscous fluids that can be non-Newtonian, what we did was modify the model to incorporate different rheological friction laws. And this friction loss includes 8 different options that range from Bingham formulations, Coulomb effects, yield stress effects, and also granular flow. And these cover a wide range of fluids that can be present in tailings dam, breaks, or also debris flow events. The ones that we used in this particular application were the turbulent, that deals with only with water, essentially, the full Bingham formulation, the turbulent Coulomb-Yield, and the quadratic formulation. So we wanted to see the effect of this. So we used the model to analyze different scenarios that could tell us how far or close we were to what actually happened in this event. So the model can, if you don't have a lot data, you have the option to enter the concentration by volume, and the model will determine the viscosity and yield stress depending on the formulas that have been found to be useful in different reports that have appeared in the literature. So it is a way to at least have a range of values for some of the parameters that are not easy to find in practice. And this applies to the yield stress, the Bingham viscosity, and also the material density as well. Now, for this particular event, we use, as I said, public data. And these two plots that were prepared by our colleague in Brazil, Adolfo Correa, he integrated different data that has been published in the literature, including relatively recent data that was obtained in some theses that were analyzed or done in Brazil. And what I'm showing here is two plots. This is a plot of the dynamic viscosity as a function of volumetric concentration. And this is a plot of the yield stress based also on the volumetric concentration of the fluid. And this dotted colored dots are the most recent one. The others that appear in black are older. But I want to point out here the wide range of values that you can get here. For instance, for the higher volume concentration values, you can get yield stress that in excess of 1,000 pascals, which is very, very high. And also in the case of the dynamic viscosity, we are talking about values that can exceed the 10,000 the 10 Pascal per second. So this is it's a wide range of values, but this gives us an idea based on the origin of the data of where we can be. And in this particular application, we found that the data near the high range of both for the viscosity and the yield stress are the values that better function in replicating the results or the observations. So what the data that we use was all obtained from public sources. We use a constant Manning's n, although in viscous flow, the Manning's does not play a big role in many of the formulations. We use a DEM, a digital elevation model for the existing conditions before the event, and one for after the event. We use initial conditions that corresponds to the dam surface that was observed before the event. And also we use downstream in the Paraopeba River a normal depth condition with a slope of 0.005 meter per meter. Then for rheological parameters, depending on the formulation that we selected, we use a range of yield stresses that vary from 200 to 1200 pascals for the yield stress, and from 5 to 10 for the viscosity. And also the material density for the water, of course, we use 1,000 kilograms per cubic meter. And for the iron core, we use 3,000, which is, as I mentioned before, much heavier than the standard sediment, because you have a large, still have even if it's a dump from the mine, it still have a higher content of iron. So these are some pictures that represents the area of the dam before and after the event. You can see the large amount of sediment that were mobilized. And this is the initial condition that we used, and also the final condition in the dam. Now, I have to point out here that one of the characteristics of the model is that you don't need to estimate the volume that was mobilized. So what we did was to just establish the initial conditions in the dam area, and then establish the properties of the fluid, and then let the model flow essentially, and let the model compute what of this amount of sediment that is contained here between this surface and this surface was eventually mobilized. And it turned out that the results were pretty good. The flexible mesh that we use, we didn't spend a lot of time in refining the mesh. We used a mesh of 382,966 cells for the complete mesh, more or less similar cells on average cell size of 7 meters, with a minimal cell size of 3.6 meters and maximum cell size of 12 meters. So it's not an extremely refined mesh, but since we were just trying to make a preliminary run, we thought it was good enough. And now I want to show you some comparison of model results with observations. So since we did all the scenarios, so with the first thing we wanted to see if how far we were from the area that was the affected area simulation. So we run the model with water, as I said. See, this are the downstream boundaries in the Paraopeba River. So these are water surface elevation, or maximum water surface elevation actually. This is the blue is the higher elevations, red is the lower elevations. This is with the full Bingham solution. So you see here the big difference. This is the final, I mean, there was no flow here according to this formulation. So, and this is typical of the non-Newtonian fluids, because when you have a yield stress, if the forces acting on the fluid are not high enough, then the fluid will not move. But what this tells us is that the Bingham formulation with those data that I mentioned before was not able to move the flow beyond this, which is obviously not realistic, because the actual flow of the mud got into the Paraopeba River. So the next one we did was with the Coulomb-Yield Stress formulation, and in this case we got a much better depiction of the area, and also with the Quadratic was very close to the Coulomb-Yield. Just to remind you, this is the actual impacted area as in the satellite image, and I'm going to show you again. If you see the Quadratic one, the results of the Quadratic formulation with the model and the impacted area, you can see here the differences, or where the model better represents the areas inundated. So let me point out, for instance, for this area here, or this area here, you see that the area that is represented in the model or resulting from the model is pretty accurate. This is the model in this area here is probably over predicting a little bit. Also a little bit here. Downstream is pretty close for the most part. And then, of course, the Paraopeba River. So in terms of the affected area, the model did a good job in many of the areas. This is another representation of what was the observed and simulated areas in the Alberto Flores road. But in terms of the total results, I want to show you a table that represents the observed area versus the resulting area from the river flow to the and the percentage errors. So you see here for the water event, the difference is very high. You have a much higher affected area. So if you, and we presented this to have a way to compare with a purity water. We have seen some applications of other models where they say, well, water is a proxy for the fluid, and let's see what happens. So in our experience, if you wanted to use a water event to simulate this kind of phenomena, you will get a very, very conservative estimates of the areas of inundation with errors in our case of more than 50%. Only in the area, but also the depth are clearly underrepresented in the water flow. Now with full Bingham, we get a much less error, but still we are about 12% off. But with the Coulomb-Yield and Quadratic, we get pretty good results that are very close to the total area, as I showed you before. Now, in terms of the actual depth, since we use public data, we didn't have measurements per se, so we use images and also proxy data that we could use to try to compare with the model results. And this is the Alberto Flores road, and in this case we have this image and we have people here, so we could estimate and we have a house. So we did an optical approximation here to estimate the observed depth, and we found that this could be between 4 and 5 meters, and the average cross section here for the model results gave us an average depth of 4.8 meters. So it was pretty close to this, and this is a point that is several miles downstream from the dam itself. This is the Alberto Flores, so it's a little upstream from the Rio Paraopeba confluence downstream. Now we also did, we wanted to compare also timing, and to compare times, it happens that there is a gauge on the Paraopeba River here downstream from the dam, actually upstream from the confluence of this river with the Paraopeba River. So the mud came here, and what happened is that the mud blocked to a certain extent the river here before being washed away by the river flow, and we wanted to see if the gauge was capturing that blocking, and if so, how we could use this data to compare with the model results. So we did a cross section here, and then we wanted to see the timing. So this is the data. So we have, this is the dam, this is the Paraopeba River. The Alberto Flores is the same name of the road, but it's the Alberto Flores gauge is around here. And this is the data that is also public data obtained from the government of Brazil website here. It's a pretty good site, by the way. And we could obtain the arrival time. And you see here, this is the level on the Paraopeba River, the water level. And you see here that up to more or less 12:40 or so of January 25th, then we have more or less normal flow, but then you have an increase in 5 meters. So what happened is that the dam that was created by the obstruction of the mud on the confluence was so high, so that the river had to increase, was stop here, and the depth increase by 5 meters until it was flushed away again. So this is again the data with more specific details. So about 12:45, you start to see the effects on the Paraopeba River, and then at 2 hours 15, you have the peak, and then it starts receding after that when the dam or this mud from the iron core from the mine starts to wash away by the river. This is a video that we created using the user interface on the QGIS environment of the model, and we can see here how the cross-section elevations evolve in time. So we can see exactly at what time this part of the river starts to increase, and we could see that at about 50 minutes from the dam failure, the flow starts to increase here in the dam until the dam that was created, and then until about 2 hours. So it is it's not exact, but it's pretty close to what it was observed in a gauge. So we could see that the actual flow that reached the Paraopeba River was at about the same time that it was observed in the gauge. Other tests that we did included the comparison of the timings in the upper side or near the dam itself. So what we did here was to find a point that we could get the the exact location, and since we have the times here on the video, we could compute the velocities or where the frontal wave from this event could reach this location here. So we did this by starting the flow and just comparing what happens. These are not occurring at the same time, but I mean both animations. But we could see when the flow in the model was reaching the same point as in the reality. So what I wanted to show you here is that the initial dam is collapsing here. So and we are giving this only as an initial condition. So it's interesting to see these waves as well, that we could also observe these waves in the reality as well. So I think was we were quite surprised and positively surprised by the model results. And with this, we also computed the mobilized volume from the dam. The observed was 11.7, and the actual simulation was 11.66. And also the arrival time to this location, according to the optical analysis here, was 23 seconds. And in the model was 21 seconds. So it was pretty close. So just some closing remarks here. From this, I mean, this as I said, this wasn't an actual project. It was an exercise to assess how the model was able to represent a real event. So in our the lessons learned that probably we got from this is that assuming water behavior greatly overestimates inundation and underestimate depth. So it shouldn't be used as a proxy for tailing dam breaks. The Bingham rheological formulation in this particular case also overestimates the impact area close to the dam, but underestimates the runout distance by several miles. So it's an issue you have to keep in mind when you're trying to use a model. one of the advantages of RealFlow 2D is maybe that you have 8 different rheological formulations that you can select to. So if you have the data for the site, then you can use that data to select which of the formulations you better represents the reality in your case. The quadratic and Coulomb-Yield rheological formulations provide the best results when compared with observations. And the model was able to accurately reproduce the tailings volume with error of less than 1%. And this is, I think, is remarkable because we didn't use any assumption in terms of the volume that was mobilized. The impacted area was around 3% difference with respect to the observed one. The frontal well arrival times have an error of about 6%, and the mud depth in the points that we analyzed were pretty close to also with errors of around 2%. So, well, as I said, we were pretty impressed by these results, and of course, you have to keep in mind that it's very important to have proper data for your case. So for prediction purposes, the better you know the sediments or the material that is deposited in these tailings dams is pretty important. I have to mention also that the Flow2D GPU version in this case runs about 72 times faster than the one core run, which it's significant because in this case the model runs in about 5 minutes or so. But if you were to use a non-parallelized version, it will run many times slower. I think one of the advantages and also the lessons learned from this application is that the model can provide significant support to improve emergency action plans for mining dams. And this is probably the best takeaway that, you, no matter what you do, you will always need to account for the damage that can occur in a given dam downstream. And tools like this can give you not only the estimates of the area that can be affected, but also timing that is critical for these events. Of course, the areas that are very close to them have very little time, but some towns that may be half an hour downstream or so can benefit from knowing that the event can reach them at some times, and then the emergency plans can incorporate this information into their design. So that's what I had for to give you for today. I have some other animations that we can create with the model, and these are created with ParaView, a tool that the model also generates the files necessary for that purpose. So okay, so let me try to answer some questions here. Let's see, what time is it? Okay, I can answer a couple of questions. Let's see. I have a questions in regards to comparing the results. Bingham has a bigger area than Coulomb or Quadratic, but the mud stopped upstream. Yeah, in the Bingham formulation, the runout was very short, but the area that covered was much larger because the depths were much more higher. So it covered more area in the upper part. So adding one and comparing with the other, you find out that the covered area upstream is higher because of the higher depth and the extent that the higher depth generate upstream. for the case that you would have no data to compare the model results to, how can we find the best rheological model? Well, in our experience, the best way is to understand the property of the deposits. So if the deposits are very wet, you have a high water content, then you would be trying to use maybe a simplified Bingham model or some kind of other rheological formulations that deal with more dilute models. If you are more toward the dry deposit, you can go to one of the Coulomb type formulations or even the granular formulation. So understanding the data that you have for your material is the key to select the rheological formulation. Okay, I have a question in regards to the stress and the shear stress. I have the yield stress. I presented the yield stress that we used was 1200 pascals. We did a kind of calibration. We analyzed different values until we got the closest results to. So we did kind of calibration in terms of varying the yield stress to represent the stoppage of the fluid, and also the viscosity to be on the on the ballpark range of the viscosity for this material. I have a question in regards to the Mudflow. If it considers erosion and deposition. It considers deposition but not erosion. We are presently working on a new version of the mud and debris flow model, and also the sediment transfer model that will include erosion for the hyper concentrated friction fluid, but that will be available probably next year. Okay, I have a question. Oh, Lionel, hi. Good to see you're here. Long time no see. I have a question by a good friend. Have you tried any modeling of subsequent river flow and potential flooding based on river course in its present condition? No, we haven't. Unfortunately, not. As I said, we just use public information. We have very little information about the data. So, but we would like to do that. That would be pretty interesting. And a final question I have here, what did you assume initiated the failure of the model? We didn't do any assumption other than the initial condition. So we assume an initial condition for the dam, and that surface that you can set in the model has the upper elevation corresponding to the pre-event elevations, and the lower elevations you can set them on the dam itself as low as you want, and then at time zero, that's the initial condition. So at that time you start the model, and then that fluid that has the properties, the yield stress, the viscosity, and the properties corresponding to the friction that you selected, start moving, and that's what essentially creates the break. So there is no other assumption other than the initial condition to represent the event. Okay, so that's all I have. I thank you very much for those interesting questions, and also for attending the webinar. again, the webinar will be shared. The recording video will be shared in an hour or so. So thank you for attending, and see you in next webinar. Bye.